All right, so the record has begun. Going back to the example screen. Okay, so here we are. You know, generally, we don't get to investigate the load carrying capacity of the beam much, especially the steel beams, because we already have the sections ready. And in fact, I will have the special table given to you that will be extremely useful, I hope. And then you don't have to struggle with the steel section anymore, because as far as we're concerned, the steel section is the section that is made from the factory. You know, it's been prefabricated. We already know how big they're going to be, and it's kind of pointless not to know how much load it can carry or they can carry, right? So the problem should be just the design. Okay, this time, wow, I don't know why it's a LIFD problem, but you know, it's just the same. Okay, so let's say whenever you see this is MU, okay? So MU, that means you must know right away that it is LRFD. If you identify this as an ASD problem, you are very, very wrong, okay? And remember that our rubric say that if you fail, oh, somebody call me now. Sorry, my phone is not with me anyway. If you fail to identify the proper philosophy, it's fatal. Okay, so when you say MU, you should know that this is LFD. You cannot use ASD. Okay, and I didn't write this down, funny how, but our beam shall be a simple beam with the uniform load. We don't need that, right? Because we already know MU, 12 meters long. Okay, so now we know MU. We know that we have made the decision to use SS400. And let's say we know that our beam is laterally braced. If we know that beam is laterally braced, no problem, because you know you are going to get to MP if your section is compact. But if you don't select any section, there's no way to know whether or not your section is compact, right? So you got to pick one first. So now remember that our general concept is that our resistance should always be greater than or equal to the load. And in this case, our resistance is VMN, right? It should always be equal or greater than the load, which is MU. So if I can say my nominal moment is Fy Zx, so this becomes V multiplied by Fy and then plastic section modulus about the x-axis, right? It should be equal or greater than Mu. And that means I can now say my plastic section modulus has to be greater or equal to Mu divided by phi Fy. Correct? So that's pretty easy, you know. So your Mu is 75 ton meter. Now all you have to do is just to take care of your unit, okay? 75 is in ton meter, but you're probably going to pick the section with the plastic section modulus in centimeter. So we better change this into the kilogram centimeter unit, right? I can easily do that by multiplying with 10,000 divided by 0.9, and my Fy is 2500 kilogram per square meter. And I get this equal to 3330 cubic centimeter. But now, because I haven't given you the table that the data is sorted by plastic section modulus just yet. So if you don't have that, it's going to be a little bit painful, but you will. Okay, so don't worry about that. I can swap to that table to show you that if you have this table, still a little bit messy, right? What you are looking for now is the plastic section modulus here. All right. So let's say if you use this table, you need to enter the table and look for the section that has plastic section modulus greater than the number that you just calculated. So right here, it just goes down to, okay. We are getting a lot more and we will see, okay, we have that. See, that is 500 by 300 by 150. Okay, but you should continue to look, because sometimes, many times, if you pick the deeper beam, it is lighter with greater number, because the depth will help increase your moment of inertia and your plastic section modulus as well, right? So you see, you can probably, okay, the first one I find, that's 500, 300, it's 150 kilogram per meter. But you can move down, you can also see, actually, I can also use this, right? And it has greater depth and it's also lighter. So you see, in this case, it is pretty clear that 600 by 200 by 120 is a much better option than 500 by 300 by 150. Because not only that it is lighter, but it is also deeper. So if you move further to investigate the moment of inertia, you will see that the 600 by 200 by 120 also has a benefit of having greater moment of inertia as well. See, this compared to that. So let's say if deflection becomes the issue, this one is likely going to give you a better value for deflection as well, and also lighter. Okay, so you can notice that this is lighter because you see the web is sort of smaller. I'm sorry, the flange is smaller. It is not as wide as this. 500 by 300, you know, the flange is pretty wide and the flange is pretty big, but the section itself is not very heavy. So even though in terms of number, it is good enough, but you say, if you can buy a car with 1 million baht, why would you want to pay 1 million and 200,000 more? Right? That's the case. And this is the beauty of design. You cannot say a person who picks the 500 by 300 by 150 is wrong, but he's just not good engineer. That's all. Okay. So I can say that, and when I pick the section, I also have this value readily available. See, you see that it's pretty low, 5.03. It's gonna pass for sure, right? But let's check anyway. So we are back here. So let's say we try H 600 by 200 by 120 kilogram per meter, right? And you say that your BF over 2TF is equal to 5.03. If you can recall your value of 0.38 square root E over Fy, maybe I should say this is lambda P, okay? That is 10.8 from previous calculation, if you can recall. So this is less than that, it is compact. And H over TW, here we go again. Okay. All right. And H over TW, even though you know that, oh, it's going to be compact, but let's complete the job, okay? 43.5. And this is lambda P of the flange, okay? And lambda P of the web, that is 3.76 square root E over Fy, and it is 107. This is way less. So you can say this is compact. This is compact. Therefore, it is compact section. And you can now see that your phi Mn, therefore, is going to be equal to 0.9 multiplied by Fy multiplied by plastic section modulus, which I didn't write down, but we got that from the table. How much it is? 3430, right? Now let's go back to look at that. Yeah, it's 3430 there. So that's it. Come back here. That is. Sorry. 3430 it is. And I can divide it by 10 to the power of 5, and I will have 77.2 ton meter roughly. So you should say phi Mn is equal to 77.2 greater than 75 ton meter. So you have the big, okay. So in terms of, you know, the points when you work and say in the exam, you need to perform the points will come from the analysis, right? If the moment is given, that means you get the free ride on the analysis, you don't have to do anything. But if you are required to do the analysis of a simple structure, like a simple beam in this case, you should be able to carry it out. Okay, so that's, if I'm not mistaken, it's about maybe 20% of the weight of the problem. If you can, you know, identify the criteria correctly, the criteria would be, you know, the design philosophy that you should use and the material that you should use. So that's the criteria. Okay, so if you use the right Fy, if you use the right design philosophy, phi, and factor of safety, that's another 10%, I suppose. And if you can identify all failures without any calculation, for example, you need to know that you have the local buckling and global buckling for the moment, and generally we should consider the shear too, you know, in the beam, but we haven't mentioned it. You should include the shear as well, and then deflection if it's applicable. If you can identify that, you need to check this without any calculation. That's another 10%. So that means if you can identify the failure, if you can identify the criteria, if you can perform the structure analysis, you are right on the border of unsatisfactory. That means you already get 40%. 50% will come from your calculation, you know, whether or not you can calculate your moment correctly, whether or not you can check your local failure correctly, whether or not you can do this correctly, and whether or not you can carry out everything correctly, which is 50%. And if you can summarize in the end that this section is safe, you can use this section, that's another 10%. That's how you get 100%. And if you can do further, say, I picked this section because it is lighter than 500 by 300, but it has more moment of inertia and more plastic section modulus. If you can pick the proper section and state why, you get extra 10%. Extra 10% for, you know, good engineering judgment. Okay, so from time to time, there'll be someone who can get 11 out of 10. So I love giving extra credit. It just, sometimes you don't need to do this, but if you can do this, if you can say, notice that it can go one better, why not, right? But for those who cannot go beyond what is expected of you, you should get 100%. This is beyond what is expected of you. It's if you can build your good engineering judgment, you should get more than 100%, if you ask me. Okay, is there any question? No question, because like a piece of cake, right? So let's go. This time it's a real design problem. And this is what is likely the thing that you will do with your design project. But this time I give you the real floor, okay? And let's hope that nobody has the issue with the superimposed load anymore, okay? All right, so this is real work. Let's say here in the problem that to select the lightest filler or secondary beam for this. So right here, this is your secondary beam, right? This one, this one, this one, and this one, okay? The one in this direction, this is a primary one. We don't do that, okay? We're gonna do the secondary one. So the filler beam will be, in fact, these 4. But let me say these 2, okay? Sometimes you can see that this filler beam or the secondary beam will carry the floor, and this becomes a tributary width for that particular beam. Let's try to put it in the middle, okay? So that this becomes the tributary area that our secondary beam has to carry. And you should notice that this beam will be exactly like this beam, the beam that we are going to design. And you also may notice that, this beam should be like, it carry 50% less due to the tributary area. So yes, but it depends on, you know, so many things. Sometimes you would want to change the size and use a lighter one than this one, because apparently it carries like 50% less. But sometimes if you know, even though it's 50% different, but you end up with a not so much different section, you may as well use the same section so that the construction is easier, because you don't need to worry about the size of the beam and so and so. But anyway, our design example here will focus on this beam. This is your secondary beam, and this is your tributary width. Two meters. Okay, this is the list of the load that this beam has to carry on this tributary width. Notice that the load is in load per area. If you multiply it with the tributary width, you will get the uniform load acting on your beam. Okay, so let's say after I pick the floor and so, the weight of the slab and the deck is 200 kilogram per square meter. The weight of the finishing is 100, and miscellaneous, it can come from anything, you know, the ceiling, the piping system, the conduit, whatever. It's another 50, okay? And the live load is 400. So for those of you who still are curious about the floor, let me do it again, that this is super imposed, right? Load. You sort of superimpose it on the floor. So that doesn't include the weight of the floor itself. And sometimes you see someone may call this superimposed dead load. Okay, so just you know that they're different. And when you do the LFD, for example, you know that you need to use two different factors for these two loads. Okay, but that's my load, and I think I'm gonna use the ASD, so I don't have to worry about the load factor, but I have to use the right load combination as well. So let's say, to be fair and to make things very clear, I would say the uniform dead load to me is the slab and deck 200, the finishing another 100, and then the miscellaneous 50 multiplied by the tributary width, which is 2. So my uniform dead load is 700 kilogram per meter. Okay, let me erase this. This comes from my hand. And then we have the the uniform live load. That is 400, correct? Multiplied by the tributary width of 2. So that gives me 800 kilogram per meter of the uniform load. So if I am going to use the ASD, my load combination would be uniform dead load plus uniform live load. And that is about 1500 kilogram per meter. Now, this is not a load summation for the column. So the next question would be, should I assume the load of the beam? Should I include the weight of the beam in my design? I say yes. And I have my very own magic number that I would assume the beam weight about, say, 100 kilogram per meter. You said the previous example, like H 500 by 300 or 600 by 200, it weighs like 120, 150. That's a huge section. And generally they are made for the long span beam, We have like only 5 meters long beam, so I would say 100 would be enough. But, even though you have to pick the section that it is heavier than your assumed load, there's no need to kill yourself about over it. You know, you can always proceed and try if your selected section would work. It may work, because you see that in the end, look at the load of the beam compared to the load of the floor that the beam has to carry. It's like, not even 10%. Okay, so now we know the load, we can calculate the required moment. It's my required moment. MA would be equal to WL squared over 8, right? This is the analysis part that you may be required to carry out, but it's piece of cake. So we have 1600 uniform load multiplied by 5 square over 8. Now, I don't need to tell you this, but you are an engineer. You should know that this moment will come out in terms of kilogram meter. You see, 5,000 kilogram meter. Okay, and this would be if you are required to do so in the exam, this would be the 20% analysis. Okay, and now, because we are using this say one-way slab floor system, and now you know that the floor will help brace the beam. So this filler beam, the secondary beam that we are designing, will be laterally braced. So let me write it down somewhere so that you know. This case, the floor helps raise the beam. So let's say if we don't have the local buckling issue, your beam would be able to reach MP, and that would mean that we can sort of try to select our beam right away by using the plastic section modulus just like before. So now I can say that my nominal moment over factor of safety must be greater than or equal to MA. Okay, and I can say that this means it is Fy multiplied by plastic section modulus over 5/3 should be greater than MA. Or I can just say now that my Zx has to be greater than or equal to this moment, which is 5,000. Remember that's a kilogram meter, so I need to change this into kilogram centimeter so that I will get my Zx in centimeter unit. And this term, factor of safety divided by Fy, generally it is basically 0.6 Fy, right? Because 5/3, when you divide by 5/3, it's equal to multiply by 3/5. So that's 0.6 Fy. And now I get 333 cubic centimeter. Okay, now it's pretty straightforward. Once you have the plastic section modulus, oops, I'm sorry, what happened? You can go to the table. Okay, but because this example has been used for quite a few number of times, and therefore I have a summary for you. Now you can just start looking at the section by looking at the weight. And we have H 250 by 125 multiplied by 29.6. This guy has Zx equal to 366. So in terms of strength, this is good enough. And then you can move on. You see the next one in the table is 175 by 175 by 40.2. It has Zx equal to, oh, I should write down unit. Okay. It's a good habit. This is equal to 369. You see, slightly better, but it weighs more. But you can also notice that this is the square one. So it's column. It would never be, I'm sorry, should you use the red one? It would never be a good idea to use this one as a beam, because not only that it will be heavy, but it will also not be beneficial, especially when you need to check deflection. Can you guys see my screen? I write something. Oh, okay, here we go. Would not come right away. I have to stop sharing here first and then share screen again. Okay, so yeah, I noticed that my red line wouldn't go. So okay, this is the column section. So it's not a good idea to use a column in for the beams. See, there's some students always, you know, they just pick the section because see, I got my calculation correct, so I'm just going to use this section. So what? That's right. It's not wrong if you you know say you're going to use it, but you would never be considered a serious engineer, proper engineer. Let's say, you know, you are going to build a small structure for KMUTT security guard at the main door. Okay, they will stay in the small structure that provide them a shade from the sun, and you insist on using the huge pile that can carry the load up to 50 tons to support their little shelter. So in terms of number, it's not wrong, you know, but just nobody uses it. And you will be considered, you know, you'll be a laughing stock behind your back because you use improper section. So don't use column section for beam. It's just not very engineering at all, even though, you know, your structure will be fine. You know, if you are going to use it, you must have good reason. Okay, so the next one in the table is 300 by 150 by 32. It seems like a good candidate, you know. You see, it is slightly heavier, but it's deeper. You increase the weight only a small number, but the plastic section modulus jumps up to 475. Okay. And now let's move on to the next one. The next one in the table, you will see 200 by 200 by 49.9. So that again, that's another column section. So we're not going to use this one. Okay. See, it's very, very heavy. And if you look at the plastic section modulus, yes, it increased somewhat, but no, not that significant. And let's move on to the next one. 300 by 150 by 36.7. So the weight is a little bit more than this, but still a lot less than 200 by 200. With plastic section modulus larger, So, you know, say this will pass, this will pass, this will pass. But, you know, let's say, what would be your choice? You know, because generally we should always check the serviceability as well. It goes along with the beam design. So I would say this one would make a very good candidate in this case, because it is only slightly heavier than this, but it probably gives a much better value in terms of plastic section modulus and in terms of serviceability, which is the calculation of displacement as well. So let me be fair and give you the value of the moment of inertia as well. But you know, if you are engineers yourself, this is the value that you should you know, check. Okay, you just don't say, hey, the teacher never gives me the number. You know, you should not. You should stop considering yourself as a student. You should consider yourself as a young engineer, you know, the apprentice. All right. And the moment of inertia of this section is 4,050 centimeter to the power 4. This one has 6,320. And the last one, 7,200. Okay. So this is much more beneficial, even though the middle one seems to be okay. All right. So this would not be a bad choice. It seems like a proper choice for me, but this is also a very good one because it is only slightly heavier. Okay. So after you pick this, so let's say I'm going to try H300 by 150 by 36.7 kilogram per meter. I'm sorry, per meter. Okay. So again, after you pick this section, you sort of investigate the local buckling, right? What did I write down before? I didn't write anything here. So, and I write compactness there. So whatever, and this time I'm going to write the third word so that you have like more option. Okay, let's say A, local buckling. Okay, and we have the flange. It's a BF over 2TF. Again, you can take this number from the table. That is 8.33. And because we say somewhere that we are going to use the SS400, so this will be compared with the good old value 0.38 square root E over Fi, which by now you realize it's equal to 10.8, 10.9, something like that. So this is less. Okay, so it's a compact. Oops, sorry. Compact section. Oops. And then the web. Again, you can pick the H over TW from the table. And that is going to be equal to 39.4. We compare this to the very huge level limit 3.76 square root E over Fi. That is 1 or I'm sorry. How come I have the different number here? One moment. Yeah, right. It should be 107. Okay, my note is wrong. So again, this is much less. So compact section again. So you can conclude that you have compact section. And you can also say that your nominal moment is equal to mp, right? And then we go to check the global buckling. You can say global buckling, or let's erase this. This time, because your floor is fully braced, so your Mn is equal to mp, and that is equal to 2500 multiplied by 542. Okay, if I divide it by 100, I get like 1.20 kilogram meter. The number may be a little bit off if you do the calculation yourself, because I seem to have taken this number from a different table, but it should be close enough. Okay, and this is, so you can conclude that your nominal moment is greater than your MA multiplied by a factor of safety, right? That's what we calculated before. But that's fine. I didn't. So let's say, sorry. Let's do it properly. Oops, wrong one. The M nominal divided by factor of safety should be, you know what? I don't have a calculator with me. It seems the number is, so if you can help me out, okay? Divided by 5/3, this should be, I don't know if that has been, the factor of safety has been included in the number. So let's, 1 second. Okay, generally I would bring down the calculator with me, and then I didn't use it. So, okay, not today. I'm not gonna bring it down and then kind of use it. Okay, so that would be
4,872.
Right. Actually, that number is included. It includes the factor of safety. Right. So sorry. This number is this one. Okay. And therefore, this one is this already. Actually, it is, it's 3, not 2. Oh, damn. Which is greater than the MA, which is 5,000. So if you do proper summary, get a perfect 10. But you should always do something extra. It's almost 11:30. We start off at 40, so that's fine. Okay, so serviceability is next. Serviceability. We need to consider the displacement as well. Okay, and now you see, the issue with the displacement is that generally there isn't any law or spec doesn't say much about displacement. Generally, the demand of, if it's not in the slide already, demand of displacement, it's the engineering judgment. think I haven't gone to that part of the beam yet, but I want to do this first, so it's fine. Okay, so generally you may see the most common is L over 240, L over 360, and then you can have L over 500 or L over 1000. You know, these the first two are pretty common, but you should notice that this is the increment of 12, which is, you know, the US and UK approach. It's like 1 foot long beam can have 1 inch of displacement, something like that. So this is not really something with restriction, you know, it's like a rule of thumb. And Thai engineers generally use this limit for the displacement on total load. This is displacement for the live load only. And this is like the special case when you work in a factory and you want to limit the vibration of the machines. So you limit the vibration by keeping the displacement of your structure very low. Okay, so it doesn't vibrate very much. So if you work in a factory, these numbers may be, you know, obtained by looking at the spec of the machines or the equipment that you need to build the structure to support. Generally, you know, there will be some parties involved in telling you that, hey, this is the information for the machine. You need to design a structure that doesn't have the deformation more than L over 500 or L over 1000. Otherwise, my machine cannot work. So you take that in mind and and check this as well. Okay, so let's say I'd say in this case, let's say for this, let's say delta is not going to be more than L over 360. Okay, so you can now calculate the displacement for H250 by 125 by 29.6 kilogram per meter. That's going to be, you know, the displacement is for the uniform load. You guys should remember this by now. It's a 5WL to the power 4 divided by 384 EI. Okay, so for this becomes 5, and then we have 1500, right? That's your total load plus the weight of the beam, which is 29.6. And then because this is in meter, kilogram meter, so I will multiply this by meter, and then I will use the rest of the length in centimeters. So my old tricks. You guys, senior citizens, should feel familiar with this, right? And then E and then I of this is 4,550. Okay, so this one, it has the displacement of 1.51 centimeter, and L over 360, that's 5 meters long, that's 1.39. So this one is probably not good. Okay, the next one, delta for H300 by 150 by 32 kilogram per meter. I'm not going to show the calculation, but let's say delta is equal to 0.967. So it's not bad, you know, it's okay. And the last one, delta for the, let's put a comma on it, okay? For 300 by 150 by 36 kilogram meter, that would be 0.85. Doesn't look like delta anymore. So I say, actually, you know, the second one is not a bad choice, you know, you can use that as well. But one thing that you do not know now and you will know in the future is that in the market, this one, the green one, this one is easier to find than that, if I believe. That's probably the reason, okay? All right, that's it. We have got the secondary beam, we got our filler beam. So pick either one of these two, that's fine, okay? And that's the design, there's no exact answer. So is there any question?
Teacher,
Yes.
about the cost of the 3 columns, does it equal? Does it the same, or is
What do you mean?
different?
You mean
The cost.
the one that I cross out?
I mean,
This one?
price of each of the 3
This one?
columns.
Well, yeah. Well, you know what? Let me answer it once and for all. The price of the material is based on the weight. So the heavier the section, the more expensive. That's all. So that's why we try to choose the lightest section. Okay. You can see this is the weight. 49.9 kilogram per meter must be more expensive than this one for sure, because it's heavier. And this one will be more expensive than this one for sure, because it is heavier. They sell steel section based on the weight. Okay.
Okay,ครับ.
Okay. Good question. See, this is what I should have perhaps mentioned before, but I didn't, because maybe it's just like a common thing. So I feel like maybe you know it already. Maybe I don't have to say it, something like that. Okay. Is there anything else? Good spot, nonetheless. So if there is anything else, let me stop the share. And I will stop the record.